Did you get it? It's bouncing? All right. I will begin with a word of prayer. Heavenly Father, we thank you for this day. Thank you for these students. Just ask you to bless this class today, Lord, and help us to all learn something about your creation, Lord. In your name I pray. Amen. Okay, so today is lecture 25, which is on polynomials in an indeterminate. So I'm going to do things slightly out of order here before I dig into precisely what is an indeterminate. I'm going to proceed a little bit formally and assume that you know what they are, because I have been doing that all along. This example serves to show you the difference between a function and a polynomial. So the functions f of x equals to x cubed plus 2x and g of x equals to x to the fifth plus 2x. These actually define the same function. Same function on Z3. All right, so how can you check that these are the same function on Z3? It's pretty simple. You just try out f of 0, what you got? 0, right? What's g of 0? 0. What's f of 1? 1 plus 2, 3, which is 0, which is, by the way, also g of 1, right? Because that's also 1 plus 2, which is 3, which is 0. And finally, f of 2, which is 8 plus 4, also known as 12, which is 0. And you can compare that to g of 2, which is equal to 32 plus 4, which is 36, which, by the way, is 0, Z3, in Z3. So as you can see, f of x and g of x are equal for each x in Z3, right? Therefore, f equals to g, right? Yet, as polynomials, these are not the same, right? As polynomials, right? As polynomials, f of x is not equal to g of x, right? What's the degree of f? What's that? 3. What's the degree of g? 5. Are these equal? No. Are these the same polynomials? Clearly not, right? So there must be a distinction between a polynomial and a polynomial function, right? Now, a lot of the times we work with polynomials with real coefficients or complex coefficients, so this kind of distinction probably cannot be made, right? But if we're working over more interesting things like Z3, then, a distinction needs to be made. So for this reason, we would like to construct polynomials. And that's what we're going to do here is I'm going to explain to you how we can construct polynomials in terms of some explicit mathematics. So here we go. R, a commutative ring. All right. Then we can define formal power series. What's a formal power series? Formal power series over R is a function. You're like, what? You just got done telling me it's not functions. Is a function, sigma, from the natural numbers unioned with 0 to the ring. And so we write sigma of j equal to s sub j typically. And we use sequential notation. So instead of writing, we'll often write sigma as a sequence, right? S0, S1, S2, and so forth. The jth one's out there somewhere, and it goes on and on. there's a clear equivalence between a sequence and this ordered list, right? If you give me an ordered list, I can define a function on the natural numbers and 0 in the natural way, right? And vice versa. Here we say Sj are the coefficients of the formal power series. All right. By the way, interesting bit of, I don't know what you want to call this here. What's study of words? Etymology. Interesting bit of etymology here. If I'm not careful, I'll say entomology, which is something else. So Rotman, on page 236 of his first course in abstract algebra, shares with us that the term coefficient means acting together to some single end. So here the coefficients together form the formal power series. That's an interesting bit, right? Coefficients means acting together to some single end. Makes a lot of sense why we call coefficients of a polynomial the coefficients, right? Together they form the polynomial. Well, this is going to make that more explicit. The reason we say formal is there's no notion of convergence here. It's totally possible that all of the s's could be 1. We could have the sequence 1, 1, 1, 1, 1, 1, 1, 1, 1. That would be a formal power series, right? For example. Now, what's a polynomial? The set of polynomials with coefficients in R is denoted what? So up to this point, I have used this notation as if it means something, and it did mean something, right? They were polynomials with coefficients in R, and I've assumed that we know how to add, multiply, and work with these things, right? But I never really gave you a careful definition of it. We've been working in some sense kind of formally with those up to this point. And now I'm about to give you a careful definition and a construction of them using sequences, okay? But not, the sequences of a rather special kind. The set of polynomials with coefficients in R is denoted R of x like that. And so it is the set of formal power series in R such that what? Well, power series in R such that Sm is equal to 0. Well, rather Sj is equal, I've been using j, so Sj is equal to 0 for all j greater than or equal to some m. Not greater than or equal to, greater than, strictly greater than m, because I want m and what do we say if that condition holds true? If all the j's, all the sj are equal to 0 for j greater than m, but Sm itself is non-zero, then what do we say? The degree of sigma is equal to what? Right, it's equal to m. And Sm is the leading coefficient. However, to be careful, we do not give a definition, we don't define the degree of the 0 polynomial. Okay, so some finer points here. Constant, well, let's say that the degree of the 0 polynomial is undefined. So But if there is a non-zero coefficient, then we can take the largest non-zero coefficient in the polynomial, and that will define the degree of the polynomial. Okay? Another way you could say this, and I like to, and this is actually, I mean, what I wrote is, it looks a little bit technical, but a simple way to remember what a polynomial is it's simply a formal power series where there exists finitely many non-zero coefficients. Right? If there's finitely many non-zero coefficients, what's that say? There has to be a largest one, right? And so it's the same as this. So, great. Then it's just a sequence with finitely many non-zero coefficients, and so then it's a simple matter to add or multiply these things, right? How do you add sequences? So we can add, sigma and beta via sigma plus beta of j is equal to sigma of j plus beta of j, right? For any sigma and beta in this, right? Because remember, formal power series are functions. We know how to add functions. We add them pointwise, right? And how do I know, but there's a question that's begged, right? Why is sigma plus beta again a polynomial? What's the degree of sigma plus beta? It's just the max, right, of the degree of sigma and the degree of beta. Am I right? Think about it. So, I mean, what this is saying is that the jth coefficient is the sum of the jth coefficients of each separate polynomial. So well, I should be careful. What could happen? What if we had a polynomial and it's negative, right? I got to be careful. I guess the degree might not even be defined if they're negatives, right? That would give us back to the zero polynomial. Would be in trouble. So suppose that beta is not the additive inverse of sigma for the sake of discussion. You could still have the case that the leading coefficients were canceling out, right? So to be careful, we should say it's less than or equal to this. So how should we multiply? Here's how you multiply them. Sigma tau is equal to S naught T naught, and then S naught T1 plus S1 T naught, and then you've got S naught T2 plus S1 T1 plus S2 T0, Eventually, the kth one is the sum I equals 0 to k of S sub I T sub k minus I. So this is the sigma tau, the kth coefficient of it. So we can multiply, and why would this multiplication be defined? Well, think about it, right? The coefficients we're looking at, they're formed what? They're formed from products and sums of the coefficients of the polynomials sigma and beta, right? There is a largest order which appears to be non-trivial, right? And so at some point, these, the sum Si tk minus I, it's just sampling from 0, right? Because you're looking at things, either the S or the T is 0 beyond a certain point. So at some point or another, all of those kinds of sums are 0. In other words, if you take the product of polynomials, you get a polynomial. Now, at this point, you're like, well, you're calling these polynomials, but these don't really look like polynomials, do they? Right? What are polynomials built from? my point is, if you fuss with this, you can convince yourself that in fact these operations are well defined, and they keep us within the set of polynomials as I've defined them. So to connect with the polynomials we know and love, R of x, we need to give a meaning to x. What is x in this context, in this wild world of construction that I'm building here? What is x? Now, if you're like me in middle school, you'd done like this: A, B, C, D, E, F. If you get to, I think T is 20, isn't it? T is 20, U is 21, V is 22, X is 23, right? X is 24? I've miscounted. Oh, curses, maybe S was 20? You guys agreed with me. I should count back from Z. But how many letters are there? 26. Oh, okay. We could do that. Good idea. But anyway, the point is x doesn't have that kind of meaning anyway, does it, right? When we think about x in algebra, what is it? It is a variable, right? For us, for the most part, x is something we're thinking about potentially dropping a bucket of stuff into, right? Maybe it's real stuff, it's complex stuff, it's, I don't know, dead cats, whatever you think about. But as you can see here, that's not going to work for us, right? X is not a variable as we think about polynomials more abstractly. That viewpoint lets us down somehow. So this is the difference between an indeterminate and a variable here. Thinking of x as a variable, these are equal. Thinking of x as an indeterminate, these are distinct. And so what I'm trying to right now build up for you is the theory of x being an indeterminate, at least a model of what that could mean. And so here's what it means. For this, x we're going to say is equal to 0, 1, 0, 0, ... 0. Actually, there's no end, is there? I should really just, ... Okay. So kind of like every good science fiction show you've ever watched, there's never really a satisfying ending, right? It's like a sequence. Now that's x. What happens if we calculate x times x? Well, if you go to the definition that's right above and look at it, what do we got? So here, let me reinterpret this for you. So here we're looking at s0 equals to 0, s1 equals to 1, s2 equals to 0, etc. Here we've got t sub 0 equals to 0, t sub 1 equals to 1, t sub 2 equals to 0, etc. So put that into the definition of multiplication, what do we get? Apparently, the 0th term is 0, right? Because 0 times 0 is 0. How about the next one? Here we've got 0 times 1 plus 1 times 0, right? Again, working it out, 0. Now, how about this one? Now, the bookends there, I think, so to speak, those are 0, right? Like, this guy is 0, that guy is 0, but right in the middle, there's the goodness. There's the 1, like so, right? What happens when we get to the next term up? If I were to write it out explicitly, what's the next term that I haven't yet written? It's what? It's s0 t3 plus s1 t2 plus s2 t1 plus s3 t0, right? That's the next term up. Do you see why that's 0? Only at this one special spot, the third spot, do we get this, both of the ones magically matching up in the same, summand, which gives us that 1. Beyond that, there's always 0, 0, 0, 0, 0, 0, all zeros. And so it goes. All right, having done this, you might wonder what is x cubed, right? Well, x. And I'm going to erase my work, all right? What do you think it works out to? If you go through this, work it out for yourself, sort through my definition, you will get 0, 0, 0, 1. And that doesn't stop there. It keeps going. Right? And this trend continues. All right? So generically speaking, x to the power, n, it's equal to 0, 0, 0, 1, 0, There are n of these. This is in the n plus 1th spot. Do we have a name for this? Well, in finite dimensional linear algebra, we would call this, if the zeros didn't go on and on, what we would call it? We'd call this just what? E sub what? I mean, this is E2, right? If you're willing to, this is E4. This is En plus 1, if you're willing to work with, sequences which are 0 everywhere except for the that one spot, right? Now, to complete this, I should show you that we can build any polynomial from a sum of these x's, right? And so that calculation I'll give you next. So here it goes. So we start with sigma, which is a polynomial, which means I can write it as S0, S1, S2, Sn. I somehow have got, I don't know, this is really something. In my notes, I somehow get to the end of the sequence. I don't know how that happened, but I guess I'm looking at the one-point compactification or something. I'm sorry, I'm an idiot. I'd rather not have written the 0 next to the parentheses in the notes here. That's not good form. I'm looking at page 144. There's a 0 right next to that. That bothers me. Okay, so here's what shouldn't bother you, is we can rewrite this as S0 and then zeros. On and on and on. And then plus S1, 0, S1, 0, and so forth. And then 0, 0, S2, and so forth, until eventually we get to the nth one. All right. And then you can rewrite these as actually S0, well, let me just write it this way. I'm going to be a little bit sneaky here and weasel my next calculation into my current one with some color. Bless you. So the thing is, you can multiply each one of these. Well, this one I can multiply by E1. This one I can multiply by E2 without changing anything. This one I can multiply by E3 without changing anything. And this one I can multiply by En plus 1 without changing anything. You can check this for yourself. If you look at the definition of multiplication, what happens if I have, like E1, which would put S0. So if I had sigma E1, what would that look like? What would E1 have for the t's? It would have T0 equal to 1, right? And it would have everything beyond that equal to 0. That would just leave you with S0 T0, which is S0. And then everything past here would actually be zeroed out, unless there was an S1 and a T0. But again, if the sigma only has the 0th component, then you just maintain that 0th component and everything stays 0 past here. So you can see that that's an identity, but I wrote up there. If I multiply by E2, right, then what happens then, if my sigma also looks like, so what you're going to get 0. You're going to get this S1 term here, and my E2 has what? E2 has T1 equal to 1, and it has all the other t's be 0. So that picks up just this term right here. Excuse me. Yeah, that term right there. No, I still got it wrong. S1, T1. Oh, I'm an idiot. I shouldn't be, I'm multiplying the wrong thing. This is what happens when you try to skip something. So the calculation, that's not quite true. Oh, fine. I was trying to avoid this, but I guess I can't. So sorry, guys. It's not a big deal. I just have to write S0 vector times E1 plus S1 vector times E2 plus S2 vector times E3 plus Sn vector times En plus 1, where S sub j vector is this. It's S sub j in the 0th component and then zeros after that. So if you take, and we were starting to see that, I see my mistake in what I was trying to do a second ago. I mean, you have to really think through it. But if you take this, right, and you multiply that by E1, for example, that's the calculation I just did. S0 times E1 gives you that. Now, for example, S1 times E2, what would that look like? S1 vector times E2 would be S1, 0, times 0, 1, 0, which would be what? That just picks up the, so I have the 0th term in the first one. Oh, I'm sorry, I'm changing, it's hard to track through it because the meaning of the S, anyway, let me stop. Enough already. This is an identity, and so what we have is the sum of S sub j vector, j equals 0 to n, and what do we've got? We've got x to the n, where we have the convention that x to the 0 is equal to E1. See, because you've got the 0th term, x squared, x cubed, What is it? Oh, that's because it's x to the j. Thank you. You're confused with good reason. Yes, thank you. And then, finally, finishing below, we drop the vector and just say, okay, so we're going to write this j equals 0 to n of sj x to the j, which is our typical s0 plus s1x plus s2x squared plus sn x to the n. Of course, here you go, the polynomials you know and love. Linear combinations of powers of x from 0th up to nth order. But, let's just take a step back and appreciate that x here is x a variable. I mean, I said, well, suppose x is not a variable, right? And if you're in argumentative mood, you might be like, what on earth do you mean? I think x is a variable. You can't take that from me. Yes, I can. Here's how I do it. I say x is equal to this. And then you say, no, x is a variable. I said, it's this. Vary that. You can't vary it, right? It's a fixed basis element. You're stuck with it. So what x is a placeholder. For a polynomial, x is a placeholder, x squared is a placeholder, x cubed is a placeholder. Really, it's just a sneaky notation for sequences with finitely many terms, and that's how we multiply them. So when you're teaching, like high school algebra or whatever, you can be like, no, it's just a sequence. What's your problem? It's a sequence with finitely many terms, and this would be helpful to no one, right? The larger point here is that we now have a careful way of defining polynomials, but this can be a secret between us, right? For elementary students that you're teaching, you probably should adopt the viewpoint that they're functions, right? Which is why that's the viewpoint I universally adopt until I get to this point in mathematics. Okay? All right, now we got these polynomials, and we can do things with them. So let's do some things with them, yeah? So the first thing we can do is define the evaluation map, right? So we say phi a of s0 plus s1x plus dot 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 plus sn x to the n is equal to what? S0 plus S1a plus Sn a to the n. You're like, haha, I knew x was a variable. This is vindication. You can plug in a, right? Well, yes, if I use the evaluation map, right? But we actually invent a notation. I mean, you could say this, if this is s of x, right, then phi sub a of s of x defines, let's say, s hat of a. So s hat would be the polynomial function corresponding to the polynomial in the indeterminate s of x. Okay? Great. Theorem. What do you think? If D is an integral domain, is polynomials with coefficients from an integral domain an integral domain? What do you think? Theorem. D, an integral domain. And does that imply that D of x is integral domain? You're like, well, if it's not true, then that's a really weird theorem. Right? So how would we prove this? Take a couple polynomials, multiply them, set them equal to 0, then what do we want to show? Right? So we want to take, say, let's let, sigma, s0 plus s1x plus da-da-da plus sn x to the n, and t0 plus t1x plus tn x to the, we shouldn't use the same degree necessarily. Let's say m as in mommy, whereas this is n as in nenu, and x to the m. And for the sake of not writing those again, let's say that that's s of x, and let's say that that is t of x, yeah? Suppose that these are polynomials with coefficients in D. Consider s of x times t of x equals to 0. Then by the definition of polynomial multiplication, which you probably felt like you understood better before today, right? Don't be snowed over by my construction. All I'm doing is just adding sequences on top of what you already know. It's the same rule, just written in terms of sequences to be formal. So don't be snowed over by me here. But look at this. What's the leading coefficient? And I'm assuming, by the way, that well, let me not assume that. How to say this? Oh, fine. Curses. Well, if you multiply these, what do you got? You have S0, T0 plus S0, T1 plus, I feel like I'm being too hard working here, but I'll just do it. You know, the leading, the highest term here is Sn, Tm, x to the what? N plus m. You set that equal to 0, right? This is, at the moment, I've just multiplied them. I haven't done anything yet. Now, suppose both s of x and t of x are not equal to 0. And without loss of generality, the degree of t of x equal to what? And the degree of s of x equal to what? I mean, let's just make it what I've already written, right? M and, yep.
Why is there only one thing in front of the x to the n? Or are there a lot of them?
Why, well, yeah, why is there only one thing there? Let's see here. Good question. So degree of t would be m, and that would be n. Think about it. That's the definition of polynomial multiplication. If I multiply the leading terms in the two polynomials, then that gives us the leading term in the product. Now, before I wrote the next sentence, it might not have been the leading term. That could have been 0 or something, which is why I didn't say that until just now. You know what I'm saying? I mean, until I say that these are both non-zero with those being leading terms, there's nothing, I just wrote this. It doesn't guarantee that those are non-zero, you know? And it's those being non-zero that's the trouble. See, because if these are both non-zero, and this is the leading term, what does that say about the product? Right, thus, s of x, t of x is not the 0 polynomial, right? Which contradicts our assumption that they multiply to be 0. Therefore, what? At least one of s of x or t of x is the 0 polynomial. Which shows what? Which shows that, well, concluding sentence. Thus, d of x has no 0 divisors, which means that it is a integral domain, right? I guess there's more. What else do we need about an integral domain? Technically, I should have said a couple things at the start of this proof. What? Do we know that d of x is a commutative ring? Something I should have probably mentioned. You can easily see that if you change the roles of sigma and tau here, this is equal to tau sigma. See, because the defining things here, flippity floppity. It's completely symmetric in the roles of the s and the t coefficients. This is a commutative product, assuming, of course, that the ring multiplication is commutative. The multiplication of polynomials is commutative. Is there an identity in the polynomial ring? Yes. the constant polynomial, just 1 serves as the identity, right? 1 times f of x is equal to, f of x times 1, and that's just equal to f of x for all f of x and d of x, right? So certainly polynomials with coefficients in a ring, if that's a commutative ring with unity, as all rings have, then the polynomials are likewise a commutative ring with unity. Furthermore, if that ring is an integral domain, we just proved that polynomials with coefficients from an integral domain, again, forms an integral domain. Which is nice. So let me project a few more things for you guys. Ooh. So you guys have a good weekend? No? It was a bad weekend? What happened? Like Dodgers fans or something? I mean.
So true about all of Boston sports. We cheated.
Okay, so let me get on with it here. Now, I meant to make a copy of something for you guys before class, but then Dr. Scamborges started telling me a fascinating story, and I got distracted. So, what was it about? Now you're trying to distract me. Good try. So this is the next theorem. If f is a field and we have polynomials over the field with one of them non-zero, then there exists unique quotient and remainder in the polynomials over the field, such that f of x is equal to g of x, q of x plus r of x, and either the remainder is 0 or the degree of the remainder is strictly less than the degree of the divisor g. We call q the quotient and r the remainder in the division of f of x by g of x. You should, he did develop this extended Euclidean algorithm for polynomials where it will actually compute so this will actually divide polynomials essentially. So here we're looking at x to the 5th, blah, 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 divided by x to the 4th minus 1. And he figures out basically that those are relatively prime. Anyway, you can see the q and the r and everything in here if you stare at it and tilt your head and squint. I would just remind you that this is a resource which is there, which is fantastic. I'm going to go back to my notes, hopefully without showing something I shouldn't show. There we go. All right. So anyway, the division algorithm, anyway, I have a proof of it in Galilean, which I intend to make a copy of for you guys and let you to have. It's something you should at least have in your, notebook. The proof is straightforward, but, tedious. And once you have it, you can do lots of things. Like, for example, if f is a field and f of x is a polynomial of the field, then f of a is the remainder after division by x minus a. The proof of this is very simple. If we use the division algorithm, we get g of x and r of x such that f is equal to that, right? And what happens if we plug in a? Well, this part goes to 0, right? And we're left with r of a. But what's the degree of r of a? It's smaller than the degree of the divisor, which here is degree 1, right? That makes r of x a constant, which is either degree 0, which means the constant's non-zero, or it has undefined degree, which means that the divisor is that the remainder is actually the zero itself. In either case, we have that f of a is equal to r, like that. And this is a well-known theorem of high school algebra, right? And you can also define zeros of a particular order. We say that, this is a C is a 0 of f of x if we have, when we evaluate the polynomial at C, we get 0, right? We say that the 0 has multiplicity k if this is a factor of f of x and yet that is not, right? So the multiplicity is the largest degree of x minus c that you can factor out of the polynomial. This is hopefully not a new idea to you. I probably don't have much more to say about that this semester. I think this comes back up again in 422. Now, corollary, if you have a polynomial in the field, we have a 0 of f of x if and only if, a is a 0 of f of x if and only if x minus a is a factor of f of x. I'm not telling you, hopefully, anything new. This is the factor theorem, right? So, what if, I think the point of the example here is to show you that if you don't work over a field, the factor theorem is not quite so simple. Like this quadratic over z6 has 4 zeros. It's messed up, right? It's quadratic. It should just have, what, 2 zeros, right? I have bad news for you. If you look at a polynomial over the quaternions, quadratic polynomials over the quaternions can have infinitely many zeros. So what you have grown accustomed to for the number of solutions to the quadratic equation, that's very much tied to the fact that you're looking at polynomials over a field. Over something connected to the field, like integers. Yeah. Okay. Anyway, but here's the corollary. A polynomial of degree n over a field has at most n zeros counting multiplicity. Now, I have a direct proof here by induction on the degree, but I think proof by contradiction is the nicest one. Just think about it. Suppose you had n plus 1 zeros, right? You can apply the factor theorem right here, right? Each distinct 0 gets you a what? A factor of x minus c. So if you got x minus c1, x minus c2, x minus c3, c4, all the way out to x minus c1, right? If you had n plus 1 distinct zeros, if you had n plus 1 zeros possibly repeated, okay? Then if you multiply those out, what do you got? You have a leading coefficient of 1 on your x to the n plus 1 term, which of course contradicts the degree of the polynomial being n. So it's easy to prove with the factor theorem in hand that you can have at most n zeros to a polynomial, right? And then finally, the part of the lecture I really should not shortchange, the end of it. I defined for you, and we'll probably prove this next class, but so the example before, I just factored a given polynomial using the nth roots of unity. So it's in some sense a follow-up to our discussion about nth roots of unity earlier and how they allow you to factor things. It's kind of neat. This definition is important. I will return to it next class and write it on the board and such. I'll just talk about it a little bit right here to get us started. A principal ideal domain, or PID, is an integral domain in which every ideal has the form of a principal ideal. What this is right here is a proof that polynomials over a field form a principal ideal domain. It's very simple. If you take an ideal in the set of polynomials, all you have to do is find the lowest order polynomial, lowest degree polynomial which appears in that ideal, and that will form the generator for the ideal. That's what this proof says. The rest is just the division algorithm and like a contradiction or something, but that's essentially it. F of x is a principal ideal domain. And then, again, this is essentially from the proof above. What's the generator of that principal ideal? It's the polynomial of least degree which appears in the ideal. And then this down here, I'm going back to that thing I did at the end of class a few days ago, and I'm actually establishing that with respect to the evaluation by IMAP, the kernel of that ideal is the principal ideal generated by x squared plus 1, which again shows you that R of x mod the principal ideal generated by x squared plus 1 is isomorphic to the complex numbers, but even a little bit more explicitly so here. I'll try to start next class working through these things, and then the next lecture is about how to factor polynomials. But you guys already know that, so maybe we'll just cover this next class and then just leave early, right?
You've never let us out early.
I've never let you out early.
I said you've never let us
I never would. That sounds like a challenge. I'd be like, all right. All right. You've been working on your test for 40 minutes. That's enough. Hand them in. Leave now.